the second presentation. So just to keep track with what we did yesterday, we had the Hamiltonian of the problem, which was with just repeat the definition. This was the interface between the water and the air. We had also another variable that we called xi, what was the trace of the velocity potential. I hope you remember. And we had this important quantity that is the total energy, which was written in the form of the kinetic energy plus the potential energy. And there is a 1/2. And as we explained yesterday, the water wave problem, we would like to recover that indeed can be seen as a Hamiltonian system in the form of there is a minus. This is a Hamiltonian system with a Hamiltonian H corresponding to what is written here, and the time evolution in this form. So it is not completely evident from the formula of H that indeed the left-hand side. So maybe I should say in addition that yesterday we had a formula that we were able to establish that was relatively simple. It was just calculation. We obtained a certain right-hand side for the evolution of eta and xi, or xi, eta xi. And what I would like to do today, a few things, to finish this section, is first to recover that indeed the original problem that we rewrote like this is Hamiltonian. So indeed the F1 and F2 identify to these two quantities. That's what we were the other day. So this is what I would like to calculate with you. And I should also say, maybe just to make sure that everybody remembers, that this G eta is the operator that associates to a Dirichlet data. Well, we can say xi equals the Dirichlet data on the boundary. The normal derivative, just to make sure that we remember. Okay, so we are ready. So the first lemma that we already proved, but I will remind it, is, so maybe I should go here. Okay, I'm on the wrong page. Okay. The first lemma that we already established, but I just repeat it, is that if I take the variational derivative of eta of H, this identifies to G eta xi. So the proof is simple. We're just going to see how this we're going to define. Let's say we take a delta xi, which is in L2, and we define this differentiation of H with respect to xi as its action with respect to the L2 to the L2 scalar product. So what is it? It's d over epsilon at epsilon equals 0 of okay, so that's the definition of of the variational derivative with respect to the L2 scalar product. So that's a simple calculation because H is given here, so I just have to write. So d over epsilon equals 0, so we have the 1/2. And then here I put xi plus delta xi, epsilon delta xi, g of eta, and here eta is fixed, right? It's fixed. Okay, and when I differentiate respect to eta, on one hand I get two terms. One is 1/2, so it's written here. The xi, so I put delta xi. Okay, plus xi g of eta delta xi, and all this dx. And because g is self-adjoint, we have not proved it yet, but I will let you accept that it is a self-adjoint. These are the same, so we can see that as the integral of g of eta xi acting against delta xi dx. So we identify the dxi as d eta xi. So that's the easy one, the term, right? So let's go to the second one. Maybe this one I can leave it to you because it's very easy. If I do the lemma 2, and I want to, so this is k, and this is plus p. If I differentiate p, not h, so d p d eta is equal to g eta. Right, so that's the same calculation, even easier. It's here. Okay, so, and now let's go to the more difficult term. So we have a lemma that says that the derivative of k in xi is exactly 1/2 of dx xi. So that one is a little bit less evident, so we were going to recover this. Okay. So that's the derivative of xi, and if you remember, if you go back to your notes, this will be exactly will identify to F2 once you add this g eta. Okay. So how do we do this proof? So we are going to. So we want to calculate d epsilon of k of xi and eta plus epsilon delta eta, right? So we want to differentiate respect to epsilon and at epsilon equals 0. And here xi is fixed. It will be important to remember we differentiate respect to the shape, so xi is fixed. Okay, so what are we going to do? We return to the definition. We return to the definition of k, and so what is k? We return to the definition. K of eta xi is what is written here, but I will return, in fact, to the definition with the potential. The potential tells us that was the kinetic energy, so that was integral over r of integral gradient of xy phi x, okay? And so we integrate the velocity square on the whole domain, on this whole domain. And so we want to differentiate this, so with respect to eta, make a small perturbation in eta. And for this, so we want to perturb from eta to eta plus delta eta. Okay? So what happens, we have this domain. That's a fixed, that's y equals eta, right? And in this domain, we have Laplacian phi equals 0. And the solution of this problem, I'll call it, so phi eta, well, it's phi, right? But now I'm going to modify it a little bit. And I keep here phi equals xi. And now I modify a little bit. Okay. And I have a solution here, Laplacian phi epsilon equals 0. And I should say that in the same way that this little phi corresponds to the solution of this problem, with eta here, the big phi corresponds to the phi of eta plus epsilon delta eta. Okay? Epsilon, well, I'm going to differentiate k when we change eta to eta plus delta to eta plus epsilon delta. Delta is delta eta is fixed, right? And I will differentiate respect to eta. It's like here, I differentiate with respect to here differentiate respect to epsilon, here differentiate respect to epsilon, I take epsilon equals 0. That's the definition of the variational derivative. Okay? Thank you for asking. Don't hesitate to ask again if you need something. All right, so let's go to exactly what we want to say. Calculate this d eta of k of eta plus delta eta, which is as, yeah?
So xi is, for phi epsilon, is xi now going to be the boundary at alpha?
Yes, exactly. You are absolutely right. Phi epsilon at eta, phi epsilon restricted to eta plus epsilon delta is xi. That will be important. Thank you. Because we differentiate respect to one variable with the other one. And so what is this? It's R. And here I have to integrate from, oops. And I write k, gradient xy of phi epsilon. Okay. So I want to differentiate with respect to epsilon. And where is epsilon? It is in two places. It is here, and it is here. Okay, so there will be two terms. And then I took it at epsilon equals 0. Okay. Epsilon equals 0. Okay, so we have two terms. The first term, it is when I differentiate with respect to this epsilon, and I put epsilon equals 0. So what is it? When I differentiate with respect to epsilon, I get this integral does not change. This integral becomes delta eta. Okay, so the differentiation of an integral with respect to this upper limit, low, high, and I have to replace here by epsilon equals 0. This is because I differentiate this term. So as epsilon equals 0, it's exactly phi. So I write here dx. Are we okay? And this one, so this, if you remember, this is so this is d phi dx square plus d phi dy square. And yesterday we had we had explicit formula for these quantities. We called that one was called V, that was called W. And I think I will need to write down here the V and W, otherwise we will be, because we need them. So this is the vertical and horizontal velocity of the fluid, right? At the surface, right? At the surface. And this is, so what was it? It was 1 plus dx eta square. It must be in your notes. And the V, so the vertical, W is vertical, V is horizontal, but this is this minus W dx. Okay? So we have a formula. I don't write it again, but this will be V square plus W square, where this equal. Yeah. Okay? And now we have the second term. The second term, we differentiate phi respect to epsilon. Well, we respect to this term respect to epsilon. Okay, so now I can replace this integral by the fixed domain, and now I write simply gradient phi epsilon dot d epsilon d over d epsilon phi epsilon. Okay, dx dy, but this one, since it's okay, you agree? I differentiate respect to epsilon to respect to this epsilon that appears here. So it gives me oops, there's something missing. Let me rewrite this nice better. Gradient dot, I will write it gradient phi dot d epsilon, or d epsilon, epsilon equals 0 of gradient phi epsilon, right? Okay, with me? Now okay, this phi is this one, and this phi is that one. Okay, and okay, and so now I'm going to use the green. So we need to calculate this. So I'm going to use Green's identity. So this gradient I put here, that gives me Laplacian phi, that's 0, gone. And then two boundary terms. One on the bottom, that will be d phi dn 0. So I need only to write this quantity at the surface. That will give me so integral over r. So we are on the top, and so what are the terms on the top? There I have d phi dn, right? D phi dn. D phi dn is g eta of xi, and this one that I don't know yet to compute. So d phi epsilon d epsilon at epsilon equals 0 dx. Okay. So the only thing that we need to calculate now is this term. Once we calculate this term, we'll have the two terms, and we'll put them together and get a solution. Now, we have something we have not used yet. It's your question, is that the phi epsilon on the modified boundary is the same as the phi without modification. So I'm going to write that we differentiate for C is fixed. So we have the equality xi equals phi of x eta of x equals phi epsilon of x of eta of x plus epsilon delta. Okay, so I differentiate respect to to epsilon. I get 0 equal dd epsilon of this. And here there are two terms again. There is one term when I differentiate this one, so it's d phi epsilon over d epsilon at epsilon equals 0. This one I take on the boundary. Okay. Or if you like, at y equals eta. And plus, this is exactly the one I need. And the differentiate of this one respect to epsilon here is phi. So it's although here some is missing, delta epsilon delta. And this one differentiates respect to the second variable, so it's d phi epsilon dy multiplied by at epsilon equals 0 and delta eta. All right, so this gives me exactly this quantity that I was looking for, this one, which is okay, so we are almost there. This gives me that this quantity that I'm looking for is equal to this. And here I need to calculate the d phi dy at epsilon equals 0, which is exactly W. Okay, so the second term so that was a little long calculation. The second term gives me at the end that d phi d epsilon equals 0, eta y equals eta. The term that I needed is minus W d eta. Okay, so we put together all the terms we need. We have this one, oops, and this one. Where is it? And this one. This one where the box has been replaced. So finally, we get dk d eta applied to delta. So the action of this derivative on an element in L2 is, well, the sum. And when you do this calculation of the sum, well, it's here, you have to take the W square plus V square plus W, so right, this one is equal and when you put all these together, you get exactly this lemma 3. Sorry, go ahead. Mm-hmm. Here? This one? So I differentiate this equality respect to epsilon at epsilon equals 0. So 0, okay, and I have epsilon in two places. I differentiate here and here. So I have to have two terms. So this one is exactly d phi d epsilon, but taken at the point x, comma, eta, epsilon equals 0. And then I differentiate, because everything has to be taken at epsilon equals 0 at the end. And then when I differentiate this one, well, I take this, that is, in fact, I could put, well, it should be phi 0. Maybe this is what you wanted to say. You could put phi 0, phi, at epsilon equals 0, delta eta, okay? Or you can put it phi, and that's w, but at epsilon equals 0, that's w. Okay? So this term is exactly this term. Oh, it's a minus, yes, minus w delta. Okay? And when you add everything, they work out to get the result. Okay? You had something else?
Yes, no, it's just why phi FCS, it's a W with the same.
You convinced now?
Yes, yes.
Okay. Okay, good. So this is the derivative. So you see, it's not so hard, but it still needs a little bit of work. And so what is missing in this chapter 2 that I am was trying section 2 of my plan? There are several. There are several things. So let me write what I would like to finish for this chapter 2, and comment what is what we have done and what is not done. So from this calculation, I would like to interpret the notion of shape derivative of the Dirichlet-Neumann operator. So it's not a trivial calculation to calculate the shape derivative, but so what I will do is that I will state the precise theorem, that I will take it from David Land book, or in fact it's in other papers of David, because it's an element that is very important when you establish local well-posedness, because you have to linearize the Dirichlet-Neumann solution. So you need to linearize means somehow derivation of. So I will say the theorem, but instead of proving it, because the proof is pretty complex, I will explain from our calculation of the derivative of the kinetic energy, because no, it's not this one. Where is no, you should. Yeah. Sorry, excuse me. That was eta. From the derivation of k in the shape in the eta, since derivation comes as acting on the Dirichlet-Neumann, I will extract the formula for the shape derivative. So it's not really a proof. It's a way to understand where does the formula comes from, because otherwise it's pretty obscure. What is the formula? So this is what I want to do. Then, unfortunately, I'm not doing things in perfect order. Then I will do I would like to discuss the property of G. I should have done this property before, but this is a direct consequence of this Hamiltonian calculation. So I thought I'd do it in this, because we still have all the formula. And finally here, I would like to also discuss the conservation laws. Because I told you yesterday that once we have this Hamiltonian set framework, we can obtain this conservation law almost automatically. Okay? So this will be the end. This will be the end, essentially, of chapter 2. Okay? So let's start. I would like to expect the shape. shape derivative. So let me state the theorem like I need this. So this is a theorem or proposition. It's shape derivative. It's also we can see it as so we derivation with respect to the surface. Okay, so the setting is the following. We're going to fix we're going to fix a function eta, and I put bar to say that it's fixed. We're going to calculate the derivative of a map that I will write in a minute. We're going to calculate the derivative at a given point. So this will be in a certain Sobolev space, to make it correct. And then, so k here will be larger than 1. So the point the point in the phase space where we want to calculate the derivative is eta bar. And the theorem says there exists a neighborhood that I call U of eta bar in this space, this Sobolev space, such that, such that for any xi, so xi is in H. So where do we take xi? It's hk plus 3/2. And now we consider the mapping. The mapping that to eta in this neighborhood. So we want to differentiate. So we get close. We are close to this. We are close to eta bar. And we consider this map that our eta associate G of eta xi. And we have not proved it yet because this property of G comes later, but we already have a sense that G is an operator of order 1. So if xi is k in k plus, this is h k plus 1/2. Okay, so this map is well defined, and it's well defined and it's differentiable. And its derivative in this sense. Sorry? This hk plus 3/2 of r is a we use 1. We use 1. It's differentiable in the sense that we can calculate the derivative at the point eta bar of G of eta bar of xi acting on in the direction, I would say, in the direction zeta. So for all zeta, so h zeta is going to be k plus 3/2. So we move a little bit in the direction close to eta bar, and this map is exactly so minus G of eta, and that's why I'm telling you it's not so evident. Xi w bar minus dx v bar zeta v bar. And what is bar? What are the v and the v bar and w bar? Okay, where v bar and w bar are the formula here where we have replaced eta by eta bar and keep xi. The xi is chosen, so we check xi we don't touch. So I don't know if you want me to just to keep the full formula. That's again the vertical and horizontal the velocity at the surface eta bar, right? So we put bar here plus dx eta bar, dx xi, and the other one. Okay, so that's what's called the shape derivative of the Dirichlet-Neumann operator. So that's that map that for xi is fixed, and we differentiate respect to eta, the map that associates to eta this quantity in the direction of zeta. Okay, and so in the proof of David and maybe other proofs too, this is a lot of work because essentially you have to return to. I mean, the method that he uses is he returns to the elliptic problem, but because we are moving this eta, it's not very convenient. He changes this domain to a flat domain, but of course there is a price to pay. Then Laplacian is not anymore Laplacian; it's more complicated elliptic operator with coefficient depending on eta, and he does this. This variation of the surface as variation of the parameter. So it's a quite a difficult calculation, but I thought since we have this formula, we're going to see if we can see this formula pops up, right? So it will not be too mysterious because already this is not that evident. Okay, so we're going just to reinterpret the formula we obtain to see how this derivative pops up. So I probably I don't need that. This we'll do later. Okay, so what have we obtained? We have obtained that if I... So you with me, I want to explain where this... I don't want to prove it, I just want to explain where this formula comes from. So, so we just obtained that if I do dk d epsilon, d epsilon of k, of xi. Okay, so we obtain that this is exactly integral of xi. No, integral. So I'm just going to. I need to copy it again. Sorry. Square, all this d eta, right? That's what we just did. Okay. And now I'm just going to integrate by parts. So when, so this is dx dx, right? So here we have dx xi, dx xi. So I take one of the dx, and I put it, I integrate by parts, so it will act on the dx xi multiplied by d eta. Okay. When I have, or maybe I will, I'm going to simplify a little bit this formula before. I will do that anyway, but I will simplify. It's so, yeah. So the 1/2. So let me put the 1/2 outside. I will simplify because I recognize the W. So I'm going to put here minus W mm, minus W. It's a little bit complicated. So I take one of this numerator because there are two, and I replace by W because that's so I hope if you see typos, just tell me because it's very easy to make mistakes. Okay, so this is the formula. We have just replaced W by what it is. And so when I see dx xc, so this term multiplied by d eta, I just integrate by part. Okay? And the same when I take this dx, and I integrate by part. So this term, it will become xc. Well, maybe let's not worry too much about the signs, but it has to be correct. W dx eta d eta. Right? So this term will give something like this. This term will give something like that. And this one, I will use that G is self-adjoint. So I can put this one. So this, it's no change of sign. That will be, so Xi is outside, and G acts on, it acts on W d eta. I'm sorry, it's not very nicely done. Something like this. Okay, I don't see. Do you see well, or do you want me to copy it again, to write it again? It's okay? Do you see it well? So at the end, we get that. I should write it once more. I put all these terms together, and let's forget. So let me put two. Equal, so I have integral, and now you will see the formula Xi, and I have to put all these so what do I have? G eta Xi, I have plus dx. That's exactly W dx eta. So Xi, this multiplied by d eta, oops, no, d eta. Sorry, I just have to write it correctly. W. Okay. So please check with me that it is correct. And so here, what do we see? This is V. Yes? There's a minus in front of everyone. Yeah. Thank you. Okay. So you see, when we had that was, you could see exactly that was 2 times integral, or no 2, Xi, d epsilon G of eta plus epsilon delta right. So essentially, by visually you see that this quantity that represents the shape derivative of G as in the direction delta eta, identify with, when it acts, I mean, acting well, in the direction of delta eta is exactly the sum of these two terms, which should be the same as the sum of these two terms. Okay, the zeta plays a role of delta eta, right? And eta here is fixed, it's eta bar in the theorem. Are we okay? So I'm saying it's not a proof, but at least it's a way to capture this non-trivial formula from the. And this is very important, as I said, for local existence. Okay, so that's a little bit the end of this discussion about this Hamiltonian, these terms and this variational derivative. I would like to, as I said here, I would like to go to the basic properties of G. So let's clean up here. So in the notes there will be many references. Well, in particular, we will try to put the pages in the books. Otherwise, it's hard to find. Yes, so I'm going to do the. I'm going to show you the expansion formally of this asymptotic of this Taylor expansion, and then I will state a theorem giving a bound of. So if you take a Taylor expansion and you want to bound the remainder, the full theorem of the spaces of analyticity, they are in David books, but they were a little bit difficult to copy because there were too many spaces to put on the blackboard. So maybe later we can talk in private. Yeah. Okay, so the property of these are the easy one. First, we start with the easy one, and the analyticity will come just a few minutes later. So the property, the theorem is these are the properties, so basic properties at least. So we assume that eta is C1. So it's bounded. It's bounded in C1, and we have a list of properties. Some are relatively simple. G of eta is a positive definite on H1 of R. Okay, because simply if I take integral of f g eta of f. Of course, we always go back to the elliptic problem. That's exactly the integral of gradient phi square. So it's always positive. Okay, second is that it's self-adjoint for the L2 scalar product. And it's essentially the same thing if you take f g of eta g dx, because you go back to the definition. And we have used it already a few times without a proof, but it's self-adjoint. The third is that if I take C and I associate G of eta C, So Xc is in H1. So this map is continuous. Is continuous from H1 to L2. And so we have, for example, the bound G of eta Xc L2, a constant that depends on the C1 norm of eta. Have this. And in fact, more generally, we have for higher Sobolev norms in HK, we have that G eta of Xc in HK. So at this point, there are many people worked on this Dirichlet-Neumann operator, and depending on the problem you interested, there are several ways to bound in HK. So maybe I'll write one or two possibility. So I'll write it here. So in higher Sobolev spaces, we have one of the bound that has been established, a constant depending on C1, multiplied by so this is a continuous C1 plus K, C H1 plus, so this is one of them, plus so this estimate, I proved it a while ago. That was so in the setting we were interested, we put these bounds for eta in continuous differentiable functions, because at that time the goal was to prove at least partially a certain validity of the approximation of solution of water waves by solutions of NLS. So that was one of the proof that the estimate that we had, and the tools to prove that was to write G of eta through operators. It was singular operators of. So it was not through the elliptic problem. It was through operators. Now there are other estimates that this one is due to C.J. Wu. At some point, she established something like this. So it was a bound. That was C.J. Wu in '87, and then I would like to mention also the one established by David Land, because that's the one that was useful for his derivation of local well-posedness. And maybe I'll make a comment about the proof. So here he writes S0. S0 is fixed. And there are two terms. One, it's a little bit like in this spirit, but a little bit different. So if you like to compare, here, so S0 is fixed. And you see, you have two terms. The first term involves K plus 3/2, it's the same order. yeah? But the gradient xc is relatively in a low Sobolev space because S0 is chosen from the beginning. And here, there is no, and here it's the same. We have xc in a high Sobolev, but it's only multiplied by this constant of S0. So there is some advantage in this. Okay, and maybe I should say one word about this. One more thing is that you can, instead of working from H1 to L2 and the scalar product in L2, you can replace that by the duality between H1 half and H minus 1 half. And instead of the scalar product, you have the duality product. Okay, so sometimes it's convenient to work in that space, and that's 1 half is reflected here. Yeah. And maybe I should say at least finally one word about the setting in this proof. So the way this, for example, this estimate is established is always going back to the elliptic problem. So essentially, you have the original problem, and you define a diffeomorphism sigma. So I think the way this is -1, this is 0, this is minus h, this is y equals eta. Okay, and by that's called straightening the domain. And if you do this, so there is an explicit formula for sigma. I'm not going to write it. You can find it in the book. But that leads to the Laplace problem, replaced by a more complicated problem. Of course, you have to pay it somewhere. So this sigma, of course, depends on eta, and it transforms the original elliptic problem to Laplace problem to an elliptic problem with non-constant coefficient, and this sigma depends on eta and phi. So here y equals 0 is c, and then yes, this is this bound, and on the bottom it's a normal derivative, but it's a little bit more complicated than the normal derivative. It involves this matrix P again. Okay. Okay. All right. So these are the basic properties of positivity, self-adjoint, and this is also basic estimate. That says essentially that the operator is over the one, but with a more specific control. Okay. So the last property is the analyticity. So the analyticity, let me explain it in this way, and then we'll so analyticity of G in terms of eta. So first of all, there is an expansion. One can calculate an expansion. So the first term corresponds to the eta equals 0 near eta equals 0. Okay, and so the important property is that each of these gi of eta is composed of so it's homogeneous of degree j in eta, and it appears as a product of eta and Fourier multipliers. So what does that mean? So I'm going to write down the first. So I'm going to write the first few terms and then explain how we find them, where do they come from, and then we'll write a more precise theorem. So G0 is the operator that we already introduced because we solved the Laplace problem on the flat. And we solved the Laplace problem on a flat band strip. So G0 is this Fourier multiplier, and I remind you that D is 1 over I dx. Okay, so that we explained the other day that essentially if you want to calculate G0 applied to a function, you have to go to the Fourier space, multiply by k tanh hk, and return back. Now G1, this is this one. So it's homogeneous of degree eta, degree 1, and it has the following form: d eta d minus g0 eta g0. But we have to, when we write a formula like this, we have to read it from right to left, meaning that if I want to understand what is g eta applied to a function f, well, it means that I have to take df, what I know what it is, I multiply it by eta, and then I take the d of the whole thing. Okay? So although people don't write parentheses, it means that we applied G0 to f, you multiplied by eta, and what you had, you applied G0 again. And G2, just because this is still okay to write it, G0 eta, G0, I don't know exactly what I wrote here. I'm not sure. Well, and then there is a 2, G0 eta, G0 eta, G0 eta, G0. So it's possible to calculate it. So it is. I'd like to show you very fast how this calculation comes up. But what are the advantages? The advantages are twofold. In numerical simulation, if you work in spectral decomposition, if you want to calculate the Dirichlet-Neumann applied to a function, if you work with the system that we were discussing, right? If this is your system, and you remember that the Dirichlet-Neumann appeared here, and you work in a Fourier space, so with spectral methods, calculating the action of G to a function, you make a truncation, you decide I'm taking 5 terms or no more, and each term can be calculated relatively easy by going back and forth in the physical of Fourier space. Yes?
For infinite depth, you end up getting the same, but with G naught.
Right. I should have said that. Yes, absolutely. Yes. If G, like this, and the rest goes the same. Mm-hmm.
Also, it has been like an hour.
Do
Do you want to do a break or?
you want to have a break? Yes, you want to have. Let's have a little break. Oui.
It's the same expression that if we do weak nonlinearity.
What do you mean weak nonlinearity?
Let's take that n-dimensional equation. I take small epsilon in front of the weak nonlinearity.
Right. Yes. Yes. You can say. Let's replace epsilon. Let's write epsilon tilde, and that gives you exactly an expansion in epsilon. And in fact, we will use that. We will use this expansion of the Dirichlet-Neumann in powers of epsilon when near epsilon equals 0, so near small amplitude, to include it into the Hamiltonian. That will give us the expansion of the Hamiltonian. Yeah, thank you. Okay, so let's have a little 5 minutes, and then thank you for and we'll say a few words how to obtain that. And as you said, this expansion are effectively very important in the derivation of the model equation, because when you take long wave, small amplitude, or that will be essentially expanding G and equivalently expanding H.